All right, hey, y'all have a quiz Monday, and I made a video already about the second set of objectives, the parametric equations and projectile motion stuff. And I said I'd make a video about just the actual graphs of parametric equations and converting them to rectangular form and identifying what conic they represent and identifying the domain and range and the restrictions on the t values, and there's a lot to this. So hopefully you'll get a lot out of this video. Let's get into it. Let's find out. Here goes. So I know up here it says identify the conic. That's probably not what you're going to do first. It would be nice if you could look at parametrics and immediately tell what conic that was. And you know what? That's actually reasonable. You probably should be able to do that. But I think it's more likely that you're going to want to eliminate the parameter and get the parametrics rewritten in rectangular form, and then from there you'll be able to tell what kind of conic it is. So that's what I'm going to do. So we're going to use that method of eliminating the parameter, which for simple parametrics like this should be easy. You could literally pick either equation and solve it for t. I don't know, let's solve y for t. So we're going to add 9 and divide by -2, and that'll give you t. And then all you do now is take that t expression and plug it in for t in the x equation. So instead of x equals 3t plus 7, we'll take all this and we'll plug it in. And I'm realizing now I probably did this backwards. Seems like it definitely would have been simpler to solve the x equation and then plug in over here, because we are getting a line, and for a line we want the whole thing to be solved for y. So I'm going to keep going just to sort of prove a point that of course it doesn't really matter. So okay, let's distribute a 3. How slow do I want to take this? Let's take it slow. How slow? You know what? Let's subtract 7. So we'll go x minus 7. And then let's multiply by a third as well. So we'll have a third x minus 7/3 equals the y plus 9 over -2. And I'm running out of space, so let me come up here. Multiply through now by -2. You'll get -2/3 x plus 14/3. And that equals y plus 9. So finally subtract the 9. And when you subtract the 9, subtract it in the form of 27/3, so that you've got a common denominator. And then you'll find that y is equal to -2/3 x. What's this? 13. So that would be the best form of our rectangular equation. We're obviously a line, so it says eliminate the parameter, It says graph this thing now. So now that we've got it, we could graph it because we know it's just a line. So we know we could plot the y-intercept at -13/3, which is what, 4 1/3? 2. So go down 4 1/3. Then our slope is -2/3, so go down 2 1/3 and down 2 1/3 and But we're going to get a line, and it goes something like that. That's about it, I guess. So again, the big... Oh, rats. My face is in the way. There you go. This is the graph. Whatever. If you guys don't know how to graph a line, you probably got bigger issues, but we were down 4 1/3, I said, because that's the y-intercept. Then the slope of -2/3 had us go down 2, right 3, and down 2, right 3, and down 2, right 3. And that gave us this line. Anyway, so looking at all this, I would assume that our equation has a domain of all reals. I would assume we have a range of all reals. And all that is true if our t value was allowed to be any real. And what you guys should definitely understand is that maybe it won't be that, right? Maybe we're going to say instead of letting t be an element of all reals, maybe t can only go between -1 and 3. And if we only let t go from -1 to 3, then at that point you might want to build a table of values and say, you know, t, x, y. Certainly -1 would want to plug in. Plugging -1 in here gives -3 plus 7 is 4. And plugging -1 here gives +2, take away 7, or take away 9 is -7. So we get a point at +4, -7. That would be like here-ish. Because what's this? That's 3. So we're like here-ish. Whatever. Then for the 3, plugging in 3 gives 9 and 7 is 16. 3 gives -6, take away 9 is -15. So that would be like much further out. Anyway, the point I'm trying to make is just that if I restricted the t to go from -1 to 3, then I'm actually restricting the line to not be a line. We'd only get a line segment now. So all this would go away. Forgive my sniffling, my nose is runny. But now suddenly, on a restricted interval of t values, you'd get a graph that's restricted, would only see a line segment instead of a line. And that means the domain and range would have to be based on our restricted t values as well. So it wouldn't be all reals. It would be x is running from 4 to 6, inclusive. And it would be y values running from -15 to -7. And hopefully for something like this is obvious. Hopefully, you know, for something as simple as a line, you guys can certainly wrap your heads around that concept, that instead of seeing the whole entire line, you just see the bit of line that runs between the sort of endpoints. And we just saw this endpoint here is associated with a t of -1. This endpoint was associated with our t of 3. So of course all we see is those points and the points in the middle. That's it. That's number 1. Looking at 2. So number 2, we can see that the x equation is quadratic and the y equation is linear. So that's a pretty strong indication that this is going to be linear by the time we're done eliminating the parameter and all that. I think in general, when you go to eliminate the parameter, probably going to want to solve the linear equation for t. So we'll get a y plus 1 all over 4. And you'll just take that, plug it in. So you'll get x equals 2 y plus 1 all over 4 squared plus 3. And looking at that, yeah, this is definitely a parabola. But the form for a parabola that we want to be in would be the y minus k squared equals, yikes, 4p x minus h. So we need to take this pink equation and get it to look a lot more like this lavender equation. So, alright, let's start off slow. I'll leave the 2 alone. We'll square this, so we'll get y plus 1 quantity squared all over 16 plus 3. The 2 can cancel with the 16, just give us an 8. And what would I do? I think we'll want to minus the 3. That'll give us an x minus 3. That equals a y plus 1 squared over 8. And really we want the y squared term all alone. And we want it on the left as well. So really let's flip-flop these and let's multiply through by 8. So we'll get the y plus 1 all squared. We'll get that isolated on the left. That'll equal the x minus 3. And we're going to multiply by 8. So we get that coefficient. So what we're looking at now is the right form for a quadratic. This is looking good. And we know that this thing's a parabola, and you should also know, if you've been paying attention, a bunch of the properties of this parabola. So I'd love for you to be able to give me The direction that it opens, well, let's just do this. First thing you got to do for sure is type of conic. And of course, that's just parabola. Direction it opens. And because it's y squared, it's going to be either opening left or opening right. And because the p value is positive, we know we open right. So next I'd ask, where's the vertex? And I'm going to ask right now, where's the focus and where's the directrix? But I won't ask for those on the quiz. Cat's out of the bag, I'm not asking. But just because, let's just see who remembers how to do it. The vertex for sure you should be able to give me. It's +3, -1. And then because we know we open to the right, if that's our vertex, we know the focus will be to the right of that vertex, and the directrix will be a vertical line to the left of that vertex. We also know that our p-value is, well, let's say it like this. We know that 4p is 8, so that means p is 2. So that means to find the focus, just add 2 to the vertex, and because we're going to the right, you'll add 2 to the x-coordinate, so it'll be 5, -1. And the directrix will be just 2 to the left, and again, it's vertical, so it's x equals. And it'll be 2 units less than 3, so it'll be at x equals 1. But there's a whole mess of information that you guys should be able to glean from the rectangular equation. Yeah, that's fine for now. Again, let's say that if you were going to graph this, you now have a whole mess of information just that you pulled out from the rectangular equation. You know you've got your vertex at 3, -1, so 1, 2, 3, -1. So there's a point. And maybe that's good enough, but we could plot a few more points if we wanted to. We know we open to the right, so you could just let x equal 4, and if you let x equal 4, that's no fun. If you let x be 4, then 4 minus 3 is 1. You'd end up with 8. Then you'd be taking the square root of 8. Why don't we let x be 5? Because if we let x be 5, then 5 minus 3 is 2. 8 times 2 is 16. You can take the square root of 16, you get plus or minus 4. And then you subtract 1 from that. So subtracting 1 would give -5. But if it's +4, then subtracting 1 would give 3. And what did we let x be? 5. So 5, -5, and 5, -3 are 5, 3, are 2 more points on this parabola. So 5, 3 would put me up here. 5, -5 would put me down there. And then there's 3 points we could plot. Just connect the dots. There's your little parabola. Again, the graph that you're looking at presumes that t can be any real number. So as long as t is allowed to be any real number, what's our domain? Our domain is going to run from our vertex to the right, and our vertex was at 3. So our domain would be 3 to infinity. And our range would be all reals. All right. Would we inherit any restrictions from the parametrically defined functions? Not really. Because looking at 2t squared plus 3, if you were to consider that function, then essentially you've got a parabola. The 2 just stretches it vertically, and then the 3 shifts it up. So we can actually tell just by thinking about this x equation that of course our x's are only going to be 3 to infinity. We can see that from the parametric equation. And for the y's, it's a line. So we're down here at -1 with a slope of +4. So for the y values, we're definitely getting a full range of -infinity to infinity. So that all bears out in the graph of the parametric equations here in this parabola. So again, the only thing we might do here is, put some restrictions on t. If I actually gave you a finite interval, then we'd start to see only a part of this. And so that's sort of important to understand. Why don't we take a moment and figure out where t0 is on our graph and indicate our direction of growth, because we're supposed to do that, aren't we? So letting t be 0 and a little t-chart. If t is 0, then plugging in 0 gives 0 plus 3 is 3. And plugging in 0 gives -1. So what's probably not too shocking to anyone is that when t is 0, we get the vertex. So that's sort of our starting point. T equals 0. Right. So there's your starting point. I guess the question is, from here, do the points get plotted as we go up, 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 and then do we come back in from the bottom? Or do we go down the bottom and then come back in from the top? Or do we sort of plot 2 points at a time simultaneously? Maybe we do that. Maybe we plot them pairwise. Let's think about it. Just let t go to 1 and see what you get. If you let t go to 1, then you get what? 1 times 2 plus 3 is 5. And over here, plugging in 1 gives 4 minus 1 is 3. So if we get 5, 3, then we can see that at that is time equals 1. So our pattern is that the points do get plotted down that branch. And what's going to happen is you run all the way to infinity, and when you get there, you start coming back along this branch. I don't know when exactly. I guess the negative numbers will do that. Yeah, the negative values will do that. But that's it. So the positive t's will run us out this way, and negative t's will actually bring us back this way. As the t's increase towards 0, you'll get the bottom half of the graph plotted. So it goes to 0 and then runs back out. I think what you see on the screen right now is everything you'd ever be expected to know. So what do? We eliminated the parameter to get into rectangular mode. Ding. We identified the conic as a parabola. We identified the direction that it opens as opening to the right. We used this form of the rectangular equation to come up with the vertex, the focus, the directrix. We drew a sketch. We can make a table of values if we need to. We can consider the effect of the interval of t values on our domain and range. Can you do all that? You guys need to be able to do all that. Okay. Okay. All right, number 3, or part C, whatever. There it is. So part C's got a radical in it. Big whoop. Let's see what that does. I don't know. What do you want to do? You want to solve the y equation, plug it in? Seems like if I solve the y equation, I'll be jamming y plus 4 under this radical, and I'll have a radical equation. I don't think I want that. So let's go the other way with it. Let's go x minus 1, and then square both sides, and then divide by 2. That'll be t. So that's getting me to a quadratic equation. I can now take that, I can plug it in over here. So I'll have y equals x minus 1 squared all over 2 minus 4. So here I am in rectangular form. Now this green equation, technically it's in a good form, I guess. It's solved for y. You should know some stuff about this form, but it doesn't really match the form that we've been shooting for in terms of conic sections. If we're thinking about this in terms of conic sections, I would add 4. Excuse me. And that would multiply by 2. And really this is the form we want. And actually I would flip these on either side of the equal sign. So the x minus 1 squared would come first. And set that equal to 2 y plus 4. Now you're in sort of the standard form of a conic section parabola. And so looking at this, you should know it's a parabola that opens. Let's see, if it's x squared, then it's an up or down. And if it's a positive coefficient on y, then that's an upwards opening parabola. Parabola that opens up. We can say with confidence that the vertex is at 1, -4. We could even do the focus and directrix bit, although this is not important. Doing it anyway. The focus is going to be above the vertex. We open up, so it's going to be above. How far above? Well, if this is 4p, then divide by 4, we see p is a half. So our focus would be at 1 comma negative 3.5, aka negative 7 halves. And our directrix would be a horizontal line, so y equals, and it would be down, so it would be negative 4.5, so negative 9 halves. So there, I've got those basics of my graph, so I could sketch my graph now if I wanted to. 1, negative 4 puts me right about there. My focus is up half a unit, my directrix is down half a unit. None of that's super important though. Let's just plot a couple more points just because. So how do you plot a few more points? Well, just plug in. If you plug in 0 for x, you get negative 1 squared, which is 1. Divided by 2, that's a half. Minus 4, it's negative 3.5. So right there. And then you could just use symmetry. Just bounce that point over. And 3 points is fine, so bring that up. This should actually be a pretty skinny parabola. This is probably too fat, but that's okay. It's fine. It opens up and it's got the right vertex. That's probably the most I could ever ask for. So there you go. Alright, here, t, nobody stipulated what t was going to be. But looking here at this radical, we know that t naturally can only take on values from 0 to infinity. Because if t were ever negative, we'd be taking the square root of a negative. So we've got this natural restriction on t. So if I did ask you about domain and range, you better not say the domain's all reals, because the domain is generated by this radical function. And that radical function only has outputs that live, well, let's see. Plugging in 0 plus 1 gives me 0, 1. So our little graph is a little radical function that goes like this. We can see we're only going to get values from 1 to infinity. So when I graph this parabola, we shouldn't see the whole thing. We are going to be very naturally restricted by the radical function that defines us to only the half of the parabola that lives from the vertex to the right. So don't show me a whole parabola if you expect to get credit. And looking at this again, this should kind of make sense because we saw a radical equation. So what we're seeing graphed is really just a radical equation. It's only half of a parabola. But instead of opening sort of down or opening to the right like we expect a radical function would, we're seeing it sort of open up. It's just kind of a reflected version of a radical function. But because we're only seeing half, this is much more recognizable as a radical function than as a parabola. So just make sure you're accounting for this. Our domain is not all reals. Our domain is 1 to infinity. Now our range, that's still going to be all reals. Super psych. I don't know why I said that. That was stupid. What I meant was our range is not affected by the restrictions on t. Our range would have been negative 4 to infinity, and it still is. So even though we're not using any negative t's, we haven't lost anything because we would have gotten all the same range values anyway. That's what I was thinking. Anyway, let's call it on that. I think we've hit all the big ticket items, so let's move on. Just make sure you don't graph a whole parabola because we do have restrictions on t. Alright, we get to the trig stuff. I think probably these we've done to death. You're probably pretty good at these actually, but let's find out. For these, you want to isolate the trig expressions. You want to get these alone. So you'll end up with an x minus a 3 all over 4. That'll equal cosine theta. You get a y minus 5 over 2. That'll equal a sine theta. And then you'll square both sides. So you'll get an x minus 3 squared over 16 equals cosine squared. And squaring both sides here gives y minus 5 squared over 4 equals sine squared. And then again, the trick here is that once you've got cosine squared and sine squared, you know that adding those together gives 1. So that'll make the theta go away and get us to only be in terms of these. So that means if I do the x minus 3 squared over 16 and add to it y minus 5 squared over 4, then that would equal cosine squared plus sine squared, which is just 1. So that gets us into our standard form. So what is this thing? Well, both variables are squared, and there's a plus sign, and there's two different denominators. So this is an ellipse. And I think I'd want you to be able to say that because the denominator of the x term is bigger, you know we're going to be oriented like this rather than like this. So you'll say it's an ellipse with a horizontal major axis. All right, for an ellipse, you're supposed to be able to give me the center, the vertices, and the co-vertices. And I think people are doing pretty well with this. The center is 3, 5. And again, the denominator of the x term tells you how far to the left and right to go, and you want the square root of that number. So with an a value of 4, you're just going to go left by 4, so that'll drop you at -1, 5, and you go right by 4, that'll drop you at 7, 5. And the denominator of the y term tells you how far up and down to go, and it's the square root again, so b is 2. So I'm going up and down 2 from the 5, so you'll get 3, 3, and 3, 7. And obviously, armed with all that information, you could graph this really easily. So we're over 3 and up 5. So over 3 up 5 will put us here-ish. You get a vertex over here and a vertex over there. You get a vertex up there, a vertex down there. Whatever. There's your graph. Who cares? Looking at it, assuming no restrictions on t, your domain would have restrictions on it because of course we're an ellipse, so we only stretch between these two maxes and mins. You can get those from your vertices, -1 to 7. And your range, we only go up and down between these two values. You can get those from the co-vertices, that's 3 to 7. So that's it. So again, I guess the question is, how would the graph change if I restricted you to a t interval of such and such? I don't know. Do I bother doing this? Let's say sure. What if t could only be an element of the set that went from -π/2 to 0? How about that? Where would that put us? I think your best way to go about this is, well, your best way is to use a calculator, and I've been ignoring the calculator, so fine, let's go do it. Boink. Boink. So there's your calculator. So you're going to do what? Clear, hit y equals. Notice that you're in the wrong mode, so hit mode. Get yourself into parametric mode. Ideally, you'll also notice that I gave you π/2, so you should probably be in radian mode, so turn that on. Now you can go back to y equals. I got a bunch of stuff in here already from the projectile motion stuff, I guess. Alright, so the equations we're working on are 4 cosine theta plus 3. And you're going to let theta be t, of course. Hopefully that's an of course. 2 sine theta plus 5. Hit graph. Alright, hey, look at that. Our window actually worked out well. First try. If your window didn't work out, you could have messed around with things. But looking at this, sure, that looks great. What are we supposed to know, though? We're supposed to know a handful of things. You might remember me saying that you could scroll over and choose this color and line thing. The color blue is fine, of course, but you might want to turn on this little tracer ball. So I hit right twice to get to this option, and I'm going to say OK. Yeah, and I'm going to go to window. I'm going to go by 0.01s so that my points get plotted more slowly. Then I'm going to say graph. Okay, that's too slow. My bad. Five times faster? Still might be too slow. Graph. Yeah, that's good. So the important thing to see is that the first point plotted was this vertex, and we plotted in a counterclockwise direction. This is going to go around about, if it was 9, then it's going about 4.5 times. So whatever, second quit. Just turn that off. Yeah, okay. So I'm back to what I can see. Slightly important, don't forget when you're graphing these things, is you're supposed to label for me the initial value. Don't forget, t equals 0. And we're going this away. So hopefully then when I restrict these values to negative pi over 2, you can kind of extrapolate what's happening. This point here would be that quarter rotation. That's going to be pi over 2. So negative pi over 2 would be here. So negative pi over 2 to 0 would be just this piece and none of the other stuff. So if we restricted our t value, all of this would go away. And what you would see is just a quarter of an ellipse, right? And how does that change our domain and range? It means our domain suddenly only goes from the center's x value over to here. So that's 3 to 7. And from this co-vertex's y value up to the center. So the lower one, so 3 up to 5. Yeah, that's all. So we would get a smaller chunk of the graph, and we would our domain and range would be affected, obviously. So if we turn, oh, the calculator is still back on. I never turned it off. Obviously, you guys can just do this in your calculator. If you tell it to only go from pi over 2 to 0, 0.01 is probably okay. That's still too slow. I thought maybe we could get away with it because we're plotting smaller bits, but 0.05 is great. Hit graph, and I think you can tell by the curvature that what you're looking at is the bottom right quarter, right? So you can do all that just in your calculator. I'm done with D. I think I'm done with D.